Imagine for a moment that cryosleep is real. You get into a small tube, a small team preps you for your journey with a variety of devices attached to your body. You go to sleep, and then 180 days later, you get yoinked out onto the Martian surface. This is the dream of President and Chief Technical Officer at SpaceWorks Enterprises, the Chief Technical Officer at Generation Orbit, and the founder of the Human Torpor Fund, John Bradford. John explains his personal journey into aerospace engineering, what SpaceWorks is like as a NASA contractor, and how human torpor, or cryosleep as it is colloquially known in science fiction, is being researched. This might sound familiar to you if you are a longtime listener to our podcast, and this is because we've actually touched on this research before in a previous episode on human torpor with Elaine Ingelson Philpula. We drilled down into the biological ramifications of cryosleep and how it might end up looking. In this episode, we drill down onto the cost-benefit analysis and what the research John is actually doing that is partially funded by NASA is actually aiming to do, and how they are able to suspend humans for up to 2 weeks. He also goes into detail on what cryosleep would look like if we did it to you, and what the space habitats that you would inhabit would look like. If you find yourself also excited about the prospects of making cryosleep a reality, you can donate to John's charity, the Human Torpor Fund, which will further enable research. You can find all of that, of course, linked down in the description. You are listening to Sci-Fi to Reality. I'm your co-host, Douglas Schoenholtz, and of course your other co-host is Michael Hladky. Enjoy.
Welcome to the show. We're glad to have you here, John. We would like to start just by asking you kind of about how you got into your work at SpaceWorks and how your life has led you here. If you could start with that.
Sure. Yeah. So I've been working in the aerospace industry for about 25 years now. So I did my undergraduate work at North Carolina State in the aerospace engineering program, and kind of wanted to continue that specialty in the space area stuff. So aerospace is pretty broad, encompasses, subsonic aircraft all the way up to spacecraft and things. So, but I was mostly interested in the space side of things. So I continued on, did my master's and Ph.D. Work at Georgia Tech, and then have been working here at SpaceWorks since that time. So that was probably a relatively new kind of idea to go out, 20 years ago. Now there's all these space startups and commercial ventures and things, but the kind of path at that time was like, hey, you could go to typical defense aerospace contractor, the big guys, Boeing, Lockheed, Northrop, or you go the government route, probably to NASA and such. But there were starting to be these small startups and things that were emerging. Think about different ways to work in the space industry stuff. So I kind of took a little bit of a leap at that time and was the kind of third employee here, and have been here since. And we've kind of continued to expand the type of work that we do, and grown the company size and engagement in the industry. The industry has shifted from what we were doing at that time to where it's now. So that's been a great thing to see stuff. So so that's a little bit of my story. So I've always been a fan of science fiction and space. So I feel like I always had the dream job. I get to work in it and kind of live it every day. So
that's good to hear. Actually, I was curious. You mentioned you guys have kind of expanded your scope and what you were doing. So how did SpaceWorks start then? If you were this third guy there, how did that get going? What were you guys doing?
So I was part of a research lab at Georgia Tech, and we were doing a lot of modeling for future space transportation systems. Everybody knew the space shuttle was expensive, was eventually going to get retired, really wasn't a sustainable way to put humans into space. So NASA was funding a lot of work looking at, they would call it second generation reusable launch vehicles, and then third generation, what was going to replace the replacement of the space shuttle stuff. So we were heavily focused on the space transportation side, doing a lot of modeling and simulation, sizing out these vehicles and what could they do, what sort of performance, and looking at new technologies, composite structures, advanced propulsion, how is that going to influence these systems, trying to go from a partially reusable or mostly an expendable rockets to fully reusable systems. So that was kind of what we started out doing. And we had some work coming in from NASA at the lab level that was probably not conducive for students. It's like we got to go to class, and they're like wanting to have meetings and things and deliverables, and we got to brief this out to headquarters and stuff. So, kind of separated that work from a research component, like this is what students should be doing. To now, this is kind of more for the industry, but they needed an independent companies to look at this. They were kind of always getting the same answers from the primes, the prime contractors, and they wanted somebody who was a little more independent. Really didn't kind of care how it was going to get built. Just wanted to, hey, let's design the best system we can, stuff. So that started of our path there. And so our first contracts were with NASA in the space transportation sector. A couple of years after that, we started doing work with the Air Force and doing work with the DoD. Generally, also focused on space transportation, but a little bit more of a military applications. Such, and then kind of grew out of that. So we're conceptual designers and systems engineering analysts, but spent most of our time doing concept analysis, modeling, and simulation type work. After about 10 years, we kind of decided we needed to do a little bit more on the hardware side and kind of take some of these ideas that we've had and let's mature them and actually start building them. So we kind of started down that path and doing smaller systems. So CubeSats were starting to emerge as a standard, and the small satellite revolution. We started looking at small reentry systems that we could build to bring things back from space, the small rockets. You see a lot of the dedicated launchers that are much smaller than the big Atlas and Deltas. Stuff that historically have been flown, stuff. So things were getting smaller, and that meant that smaller entities, smaller companies, could actually afford to go and build them. It didn't take billions of dollars to do something neat, valuable in space. You could do it for hundreds of thousands or millions of dollars, and such. So that created this opportunity for small companies, I think, to emerge and kind of grow in that sector and stuff. So that's been where we've been focused and kind of making our contributions. So
that's really cool. That's crazy how big of a range you've managed to touch then as part of SpaceWorks. That's really incredible. One thing I wanted to ask about there is you mentioned pretty early on that you guys were looking at reusable components. Are you talking about some of the stuff that SpaceX and Blue Origin are working on now with like reusable rockets that can actually land themselves, or is that like reusable components?
They're recoverable, reusable rockets, and how do you get them back? And there was always a big kind of trade space or debate within the rocket community on reusability of do you have something with wings that comes back and lands on a runway, so it lifts off like a rocket and then comes back and lands horizontally on runway, or can you do the vertical takeoff, vertical landing approach for SpaceX? SpaceX has adopted, and now Blue Origin and such, and you're seeing kind of more systems that can do that. And that was a big debate for a while. I think a lot of the Air Force liked things with wings, and wanted to pilot things in and such. Didn't mind taking off, but SpaceX kind of answered the question on that stuff. So now that is the way we approach things or design them. They're going to all propulsive landing. We don't put wings on there, and bring it back and land it on its tail, such. But that was part of the discussion, in the trades. And it's a propellant. Do you just make the rocket bigger and put more propellant in it to do that landing? And could you do it? There was concerns about the physics of rotating that big booster around, firing its engines backwards, relighting. What happens if you're doing that terminal landing and you don't relight those engines and stuff? You kind of have a mess on the pad versus, hey, once you turn off the engines on the after the main boost and you can glide stuff. So wings are passive. They don't really have to do much. Is that a better answer? So we were constantly looking at trades, and DoD had a number of programs to make small demonstrators and try to field those systems. But SpaceX came in with their solution, and that's the answer there now.
Nice.
So yeah.
So now you did all of this really awesome work on trying to build out kind of the last what is the timeline actually? I don't want to make an assumption. How long have you been at SpaceWorks, and what's that journey been like from a time perspective?
Yeah, so I got here in 2001, so just
Okay.
just at 20 years.
Damn. That's crazy that you guys have done that much in 20 years. That's really incredible. So, and then would you say, now I want to transition a little bit towards human torpor and that whole, and getting humans out into space at scale. And I'm curious, from your perspective, do you think this project seems substantially different than any of the other projects that you guys have overtaken over the years? Because it seems like this far off pie in the sky idea in a lot of ways. And do you kind of see it as like that? Or do you have other projects that are similar to it in that perspective that are that far out? Or have you had projects in the past that have seemed that way at the time?
Yeah, it's a good question. And so, at a high level, we've always part of our assistance, I'd say, to the government has been in being technology planners, helping them. Hey, the government's got a limited budget. You get all this input. We've got all these technologies. Hey, I've got a better mousetrap. I want to, my thing does this, my thing does this. And they're like, well, what do I fund? What's the best thing? So we would take all these technologies and put them on existing systems and try and say, hey, it's going to cost this much to develop that capability, and it's going to get you this much benefit. So it's a cost to benefit ratio, and helping them decide where to invest all those dollars stuff. So we've always kind of looked at, advanced technologies and, looking for that next thing that's 10, 20, 30 years out that's going to revolutionize the industry stuff. So from that perspective, no, but that was probably some of that kind of helped identify, I think, this technology. So while we were also looking at space transportation systems, we were doing missions, designing missions to Mars, return to the moon campaigns and such. So we were doing all that modeling and systems analysis, and we were oftentimes looking at, hey, you got to advanced propellants, or you've got a new engine design, or you've got these new lightweight structures, and we put that into the, we call it the architecture, and see what happens. Like, hey, we saved, 3 launches and, $5 billion. Hey, that's great. And stuff. And we play with these technologies, but generally they were, most of the technologies didn't do too much. It got better, but on the scale of things, they would only impact a limited area of the mission. And, you had to have like 10 miracles to really, revolutionize the way we were going to go to Mars or go into outer planets stuff. So all these miracles had to happen, and technologies had to mature, and then you could get something cool. So I was like, man, there's got to be something more game changing than that. And as a fan of science fiction, you see human hibernation, stasis, and suspended animation is like almost in every movie, really, right? So started researching that, and what is the current capabilities? What can we do? Is there anything that's close to this right now? And you have commercial companies that offer, cryogenic suspension, and they'll freeze you. There's a lot of caveats with that and expense for that process, but they don't have a way to pull you back stuff. So you're betting that maybe in the future they'll figure something out, right? So we said, well, what do we have now that could maybe help us a little bit in this area? So started looking in, hospital procedures and talking with some colleagues in the medical community about what can we do that's close to this stuff. And then I, through that, identified some current capabilities and things that were being used in hospitals in emergency situations that maybe if we pushed on them and extended them and, put some big aerospace dollars into these areas, that, we could use it to the benefit of human spaceflight stuff. And then with that, proposed some the work to NASA. And fortunately, they were interested enough, because I had this traceability to what you could do, that they went ahead and funded that work, and that identified. Then we started doing the architecture studies and really quantifying the benefits of it, and seeing some pretty impressive gains in terms of cost and mass reductions, as well as impacts on the human human health side of things. So, we proved out that, hey, this would be a game-changing technology. It's way better than 10 different other miracles. We
For
can
sure.
focus on this one and get all these benefits and probably enable us to
So
go into space like we want.
I think I've gotten a little ahead of myself here. So we're talking about how awesome this thing is, but let's define what human torpor for space actually is, and kind of what the research you guys have done for some of that contract work for NASA, and what it would look like if we were to ship somebody to Mars in one of these torpor states, in one of these torpor-based vessels.
Sure. So what we're ultimately trying to do, and we've identified a couple different ways that it could be done now in the research. What will ultimately get implemented may be different, but we're wanting to put the spaceflight crews that are on long duration missions in this inactive, low metabolic state. And we call it prolonged hyperthermic stasis with metabolic suppression. And we want to do that when they're in the transit phases. So whether you're going out to Mars or Ceres, such, it's generally a couple hundred days of travel time. We'd like to put you in this low metabolic state. And we think it can have a lot of benefits from both medical and in engineering. Solves a number of challenges there when you do this, and we can talk about those there. But our primary focus was trying to basically minimize the crew, almost treat them more like a cargo. It takes so much to support. That is the problem with human spaceflight, is the humans. Everything that goes into feeding them, thermal control, oxygen, health stuff, that is the challenge. So how can we minimize that and their kind of footprint on the mission, particularly the transit phases? So we've always taken the view that the transit phase is really the most benign, uninteresting portion of the mission, and we just want to get to where our destination. Nobody really wants to go, take the long drive stuff. So we want to get you there and get you there as safely and efficiently as we can. So how do we do that? So our focus has been on this prolonged stasis, and we achieve that through reducing your metabolic rate.
So you guys have done these studies on how to achieve this prolonged stasis. So where are we right now to start with? What does the timeline look like for the research to get to a point where we could do that?
Sure. And so what we've based our kind of our point of departure, we'll call it, our model, was based on a clinical procedure called therapeutic hypothermia. And they use this in traumatic brain injuries, cardiac arrest, stroke victims in the hospitals currently. So, and protocols there are, if you had one of these injuries, they would bring you in, they would cool your body down, and they would keep you in this state for 24 to say 72 hours, so 2 or 3 days. And that gives the body time to recover. It minimizes your oxygen use at the time your body's probably struggling to provide that oxygen, and it prevents any long-term damage. So, and we're only cooling you down a couple degrees, so it's not we're not freezing you and such. But the fundamentals and the approach of reducing your metabolism, reducing your oxygen demand, your caloric intake is kind of what we're trying to build off now, and adapt those clinical procedures to what we can do for space flight. So 2 or 3 days is what we have a lot of data on. Our challenge has been most of that data is for people that have been injured. So you got to separate the injury with the benefits or the impact of the therapeutic hypothermia. And there are studies now going on that are they're doing this on volunteers or healthy individuals, and they're able to isolate better what the impacts are, and basically how to optimize the system. What's the right drug or sedation levels? What's the right target temperature and such? So we're building off of that and making adaptations for space flight. So
okay, and how do you actually induce the lower metabolic rate depression? How do you actually get someone into that state?
Right. So in the clinical setting, they'll come in, they'll heavily sedate you, and then they'll do things like either put cold gel packs or a cold saline injection and start cooling your body down. So you're basically trying to enter or mimic putting your body in a hypothermic state. So, and you see this if you go outside in cold weather, or people get lost out, lost out in the wilderness and such. Your body will start to shut down and stuff. So they always tell you if you're going into hypothermia, don't go to sleep because your body is really trying to shut things down. Such there. So we're trying to do that a little more safely, a little more naturally. Stuff. So one of the changes what we're looking at is there's some new pharmaceuticals that can kind of mimic and suppress your thermoregulatory system. That controls where your body kind of wants to target temperature. You go to the doctors and they're always, hey, you're at 98.6. Okay, good. You're healthy. You don't have a fever stuff. So you have humans have a very limited range of where their bodies all operate at. So this kind of basically these drugs will lower that set point of where the body wants to target itself at. So what happens when without this, as you start to cool people down, and why we have to sedate is your muscles try to fight that. So you start shivering. They're trying to generate energy, warm yourself back up. So we put heavy narcotics to do two things: make you feel comfortable because it's miserable being cold, right? And second, really to ward off that shivering reflex that's trying to fight, warm yourself back up and make yourself active. So this helps reduce that shivering reflex as well as the body's resistance to that lower temperature stuff. So things will naturally kind of turn down. We tend to go from, I said 98.6, or that's 37 degrees Celsius. So we drop to about 89 degrees Fahrenheit or 32 degrees Celsius is our kind of target range. So it's about a 5 degrees Celsius drop. And with that, we can get a 50 to 70% reduction in your metabolic activity stuff. So not only are you kind of inactive, but your body demands, caloric demands, oxygen, heart rate, everything will drop off pretty significantly. And we can hold you in that state. So that's where the therapeutic hypothermia stuff, that's their target temperature range, 32 to 33 degrees. The body has a natural kind of limit. You don't want to go below about 28 degrees Celsius. At that point, your heart can't function. It can't generate the electrical impulses it needs to pump the blood stuff. So that's a very dangerous condition. So we try to stay above that, but get as much benefit out from the reduced metabolic demand as we can.
So if let's talk food. So my understanding is one of the big limiters is, first of all, if you're walking around, you have the higher caloric intake, and also you're probably eating more substantial food. And I understand that you guys have what's called a PEG, something that goes through the wall of your stomach and directly into your stomach and pumps food in some capacity that way. So you still use your whole digestive tract and so on and so forth. Could you talk a little bit more about that?
Yes, yeah, and that was we started out with one concept in the under our first NASA grant, and then as we talked and expanded our medical team, we have migrated to a different concept there. But that was always one of the challenges. So we like to say, humans aren't bears. We don't get to go and stock up and load up to be 1,000 pounds, and then you're going to get to Mars or wherever and be like ultra fit and stuff. So that's really bad on the body. So we do have to provide hydration and nutrition stuff during the transit when you're in this phase. But it is significantly reduced from your normal and active person. So under we call it our phase one, we had the idea of using, it's called total parenteral nutrition, or TPN, and you can do a direct IV injection of that solution. And they use it for patients in hospitals that have no digestive system, such, or oncology patients and such. and it's really like it's pre-processed food. So it's down to like amino acids and things that it's what all your digestive system is generating to feed your body. So we had started with that. That is a little challenging for two things. First, trying to get that right. You have to be, very carefully monitored, because that is everything your body's getting and such. So the other challenge is that it's hard to resume normal eating. So it takes kind of a transition period back to normal eating if you're on this TPN. So the astronauts probably don't want to deal with that, but they're probably going to want to eat some regular food by the time they get to Mars stuff. So we've migrated that to now the PEG tube. So we can't feed people and they're inactive down their throat and use their esophagus and chew food and things. So this is another medical device that's in common use for children through adults that are unable to use their normal GI tract for eating stuff for various reasons. And there's a small procedure that's done, will be done before the mission, that does install this basically a port access to your stomach. So you have a minor surgery to put the backing in it down into your stomach, and then from the outside, the kind of two seals come together, and you can have basically a permanent hole exiting or entering your stomach stuff. And from that, you can feed and provide food. It's a liquid solution, so it's kind of like a milkshake stuff there. So you're not trying to put in cheeseburgers or such there. So you need to have food that your stomach can easily digest at that point and can go through the hole and such. But very easy, very stable, and kind of safe. You can little maintenance to kind of clean it, such. But there's a lot of people that have this and have to eat this way, stuff. So we've adopted that, and it does allow the crew members to go back to just normal eating and stuff. So you can eat basically both ways and stuff. Maybe it's good. People that are constantly on the go may want to get a PEG tube and stuff. Eat your food hands free in the car or something. Yeah. So that's probably one of the more. We talk with some of the astronauts, and hey, what do you think about this? Some of them are like, I don't know about doing that. And others are like, hey, whatever it takes, man. We're kind of guinea pigs. That's fine by me, and stuff. So, and it can be removed. So it's not a permanent device stuff, and you can close it back up. I'm sure you have a small scar there from this, but it can be removed and safely done and reinstalled if need be, stuff with minor surgery. So that's where we're currently at on the nutrition and hydration is using this PEG tube. So.
Gotcha. That's relieving to know that it's like a well-established procedure. I hadn't heard of it before. So if you have a hole in the side of your stomach for the rest of your life, that's never been. That's relieving to hear.
You can find some people are pretty fascinated with it that have it, and they'll put YouTube videos out and watch me eat my dinner and pouring in a Coke into the tube and stuff. So it's very very safe, very easy. From children up to adults that use this.
Gotcha. Yeah, it makes a ton of sense. And then some of the other stuff you mentioned there, I shouldn't say you mentioned directly here, but I've researched here, and you sent me a couple of resources beforehand, was electrical stimulation of all of the muscles to make sure you don't get really nasty muscle atrophy. I'd be curious, is there a precedent for that as well? I'm assuming that if you stimulate the muscles, they'll respond, but I'm curious if there's existing literature on it for long periods of time.
Yeah, there is. And so some of the advances that we're looking at come out of physical therapy for bedridden or immobilized people stuff. So they need this sort of care and support there too. But generally, though, the muscle atrophy issue is a chronic problem in spaceflight, particularly if you're going to be in a microgravity type of environment. The ISS crew members spend 2 or 3 hours a day exercising pretty rigorously, doing all sorts of weird contraptions and stuff to just maintain some of that mass stuff. They still are in weakened states stuff when they return, particularly for the longer flights. So There's been some commercial devices that, hey, you can get your 6-pack abs, and you can put these things on it. It do work. It's not very comfortable and
Sure.
stuff, but it's a balance. So you can't just eat whatever you want and apply this and stuff. There's other elements to fitness than just flexing your muscles, right? But on the ISS, JAXA actually has done some experiments comparing astronauts using a neuromuscular on one arm and not applying it on another, and taking muscle density testing and samples to understand it. And it was they did it over a period of a couple weeks, and they show promising results from applying it in space, that it is effective there too. So there is precedent from both just a commercial applications as well as they actually have done this in space before. So the issue is that it's just not very comfortable. It's kind of irritating. It's kind of painful and stuff too, depending on if you're really getting aggressive. So part of our argument and advantage is that with the crew in this inactive state, they're not going to really be aware of this, and we can apply it, do whole body neuromuscular stimulation and activate all the muscle groups. It's just a small probe that gives you a small little electrical impulse, and your muscles will contract stuff. So we can help. It's not a complete answer, but it will, I think, greatly mitigate some of that challenge. The reduced metabolic state and reduced cellular activity, we also believe will that also helps reduce some of the muscle atrophy. They're just less active. The cells are less active, stuff too. So this is a case where we have both an engineering solution that we get to introduce with this solution, but there's also medical advantages from just lowering the metabolic activity in the body. Everything kind of slows down.
Okay. And so I skimmed over the report you guys put out for NASA. I saw that you guys were able to put people into the lower metabolic state or into the stasis for about 2 weeks. Is that correct?
Yeah. So the kind of clinical case studies, they're always looking at, with the therapeutic hyperthermia, or they call it targeted temperature management now, what are the ideal protocols? What is the recommendation in the hospital settings? Is it 32 or 33 or 34 degrees? Which one shows the most benefit and for what duration? So they've done duration studies looking at just a few hours, all the way up to 2 weeks, where they kept people in this condition. But they basically found out that this 2 or 3 day period is kind of the maximum benefit, but that's for injured patients, and they've got other things they need to start addressing. So the studies didn't really show any benefit for continuing to keep an injured person in there for more than 3 or 4 days at max. So we need to move on and solve other problems. But for patients that were in there for 2 weeks, they didn't show any negative impacts associated with that. There's just no compelling reason to do it. So hospitals are expensive. Let's get people moved on, get them back to therapy and recovery and such. So we have the limited data going out to 2 weeks. One of those studies was in China, where they were looking at it, and then there was another recent one in Germany and such, where they performed this. So there are some caveats there. They were still in hospital settings. They were for injured patients where they did this. They were doing the heavy sedation, such which heavy sedation over those long periods is a concern, particularly in spaceflight. If we're going to do this for months at a time, you don't want to be on heavy narcotics and things for that long a period. So these are some, changing the drugs and sedation approaches is one of the things we're focused on. But yeah, 2 weeks, and because of that, that's what we've established as our kind of baseline approach. Is we're going to put the crew or passengers, they would go under for 2 weeks, then we would warm them back up, they'd be active for a couple days, and then they would do it again. So there's less of a concern with repeat cycles than the continuous duration.
Okay.
So we think we can basically over 5 or 6 cycles, then you would be a trip to Mars. You would do this just repeatedly. So.
Okay. And now that we're talking about how long we can put them under, so let's talk more concrete. What would this mean for a trip to Mars? What kind of mass savings are we looking at compared to not having anyone under any kind of stasis? What would this enable us to do for a trip to Mars to build a colony or whatever we're trying to do there?
Sure. Yeah. No. And that's one of our main kind of benefits, or at least where we started this work was like, let's try and get the habitat mass. Let's try and get all that out of the system. So you got to think on a round trip mission, which is going to be the near term plans for going to Mars. Everything you send out there, you need rockets to push for bringing the crew back. Then you need those rockets. You have to push those rockets out that have got to push everybody back. And we call it the tyranny of the rocket equation. It's an exponential function. It gets harder and harder the more stuff you've got to push. And then to top it off, all that stuff has to be launched from Earth stuff. So it gets crazy massive to do that. So if you look at, we call it the gear ratio. What things can we if we reduce a pound here, we can get like 10 pounds of savings on the rocket side for doing that. And the habitat is one that's got to go all the way out to Mars, got to come all the way back. Everything's in it and stuff. So with the habitat, we can get like a 56% reduction in the mass of it. So it's smaller. When we start stripping out a lot of things that we don't need anymore with the crew in this inactive state, when we reduce the consumables, we can make the volume smaller. That translates to things like the environmental control system, the power system, everything shrinks down stuff. So it just compounds. So we have the engineering tools that can do that sort of analysis and capture those effects. And then we build up the rocket stages to then support that mission stuff. And it's, cutting the number of launches in half for these compared to a non-torpor or non-stasis crew stuff. And that's all really at the end of the day, that's probably dollars. That's budget, because those are the heavy lift rockets are, super expensive. It's risk. We got to put all this stuff up, and then we've got to assemble it all on orbit. So oftentimes you'll have multi-stage propulsive systems. So you'll have three stages just to get out to Mars. So oftentimes we can eliminate an entire stage or two. So that's one less big on-orbit assembly activity that you don't have to conduct stuff. So it just starts spiraling out all the savings from there.
Wow. So when you mentioned the habitat could be 56% smaller. So if we were to zero in on that for a second, is that the habitat in the actual rocket itself while you're transporting to Mars, or would that be like a habitat on Mars itself? Just to clarify.
Yeah, so oftentimes for these missions, all the infrastructure that you would have on Mars, so we will send that in advance. And that can go on like a solar electric propulsion stage, something that may take like 3 years to get to Mars. So you can send it very efficiently, but you don't want to put humans in space for that long time because of the radiation exposure. And then that's just more food and things to support them there. So we send all the surface infrastructure and habitats and landing systems kind of on a slow boat. It's like coming across the Atlantic on a cargo ship, and then you get on the plane and go. So that's generally the ConOps, the architecture. So all that stuff will get there, and once you set that up, most of it will be reusable. You won't have to keep sending a new habitat stuff again. So we're primarily focused on the transit piece because that's where we'll need to keep redoing that over and over again for multiple missions, for sending more and more crew and building up that. So the 56% reduction is on the transit, call it the transit habitat. So
for sure. Very cool. So this is, I'd be curious to know what NASA thinks at this point. Obviously they like you guys a fair amount. They've done a bunch of contract work, but and I know you aren't NASA, so you can't speak directly for them, but do you have like an idea of what NASA thinks about the long-term viability of this project and what they'd be thinking about in terms of getting the ball rolling with it, et cetera?
Yeah, no. Well, I will tell you, when we started, it was, I think, fairly controversial.
Sure.
So I think there was a lot of there's always a concern, like, man, this sounds crazy. What's Congress going to think when they hear NASA just funded some human hibernation? What are the taxpayers going to think when they do this and stuff? So there's that, and I understand that there's political kind of ramifications. They'll be like, cut their budget, get rid of that entire division at NASA, or directorate, because what are they doing over there and stuff? So there's definitely that level of concern. And I think a lot of internal discussions, but fortunately, a lot of people that said, no, this is what we need to be doing. This is what the type of investments we need to make, because look what it could do, stuff. So if we're going to kind of get out of this just very slow progress of human exploration, which is their mission, we need to invest in these game-changing technologies. And quite frankly, they spend a lot more money on other much more mundane things and stuff. So this is not billions of dollars or even millions of dollars being invested or such here. But that's part of their charter. So they do take a certain amount of their budget to investigate kind of new game-changing technologies, and make sure, hey, we don't want to miss something that could totally change the way we're doing everything. Yep. So we're fortunate enough that we kind of won that battle, and we're given the opportunity to really study it and through 2 rounds, and expand the medical team and bring in a lot more credibility such here, and do a job that we showed how you could get to there, knowing what we know and what we have today. It wasn't like, hey, one day when we have fusion power, then this will be great. It wasn't looking at pulling from something down the road or downstream. It was starting with what do we have, and we developed a roadmap of how to mature us. And it is also an evolutionary progress. Hey, with 2 weeks, which everybody was very confident we could do, we showed the benefits for a Mars mission with just being able to do that, within the limits of kind of reality or maybe relevance even. So it's probably less relevant that in 100 years you could do this, but if you could do it in 20 years, 15 years, then that's cool. And that, because it takes that long to mature these things and perfect them anyway.
Yep.
So the first mission, we're not just going to put people into stasis and send them off to Mars. It'll be, and these missions only occur every 2 years, or the, Mars opportunities. So it's going to be a slow process to continue to expand and collect data and stuff on it. So we can still be safety focused, but be able to do something that is impactful very early on. So it was definitely polarizing. And I think as the study went along, we got more and more interest, and like, oh, no, that's a good point. No, that's good. And I think more opinions started coming in, and it became less crazy about the, science fiction, and people got it. And okay, you're not freezing people. All right, that's good. And stuff. So, and to the point now, there's been some recent, even just 2 weeks ago, there were some awards put out, some research study awards. So NASA has a kind of a sister or an entity that they support called TRISH. It's with Baylor College of Medicine. And there's a consortium down there that put out a call to support research for basically low metabolic stasis. And they've recently made 4 awards. And I was excited about it because one of their requirements under the program was really to have a human component to it. So it wasn't like grow some cells in a petri dish, or just do some very limited animal studies. They were like, part of the requirement for these studies were to have that human element stuff. So it's definitely it's traceable, and they're branching out in a couple of different interesting areas for what you could do with this stuff. So taking time, but I think people starting to lean into it and get a little more interested. I host by judge a student design competition that NASA conducts every year down in Florida. We have 15 or 20 college teams that come in, and they're doing design and architecture work for space systems, whether it's missions to Mars or the moon, or geo and space tourism or what. But they get to pick their theme and stuff. And now I'm seeing more and more teams are doing like, oh, we used torpor, we used human stasis as part of the architecture, and it's not, nobody's like, what? So I'm always encouraged that there's, oh, okay, I see what you did there, sort of thing. It's So that's been, I think, been promising. It's becoming accessible. The information is becoming more accessible, and people are actually considering it more. So
That's awesome that it's starting to really become kind of a mainstream idea and starting to actually get it adopted into what people are seeing the future of space entailing.
sure. Yeah.
Um, could I? So, if we did a trip to the moon, would you? Sorry to change tacks a little bit. Would we still see? Would we still see some of the space savings that we'd see on like a longer trip to Mars? This is something that's been bubbling in the back of my head a little bit.
Mhm. Yeah, and that is one area or application that we've been looking at is, probably before we go and colonize or set up lots of people on Mars. That's a pretty big challenge and will take a lot of time. Um, there is a equal camps and interest in maturing the economic a space-based economy and cislunar, between the Earth and Moon stuff, and growing that. And there's talk about, hey, we're going to do heavy industry or manufacturing and energy production on the Moon, and then we just, keep the Earth in much better condition. Let's get all this, all this bad stuff we're doing. Let's get it off planet and stuff. And the Moon's a nice place for, I think, for doing that. So it's that, as well as doing like space tourism. So you want to vacation where the stuff is too, but the Moon's a relatively big place. So we would think for this torpor and stasis, eventually we're going to want to send 20, 50, hundreds of people there. And it has applications there because, again, it's still a couple days transit stuff. So if it's going to be people working on the Moon that are, doing fusion power plants and maintenance, or, heavy industry and stuff, for transportation there, it can help out. For sending large numbers of people to the Moon, stuff there. Probably don't need it unless it's a demonstration type flight. If you're going to send 4 or 6 astronauts and stuff, so I'd use it in that context. We think about it more for demonstration purposes. Before you go to Mars, you'll do a lunar kind of checkout and such there, where you could get people back easier or fix things and such. So, but for really advancement on the Moon and sending people, I think it has a lot of advantages. You wouldn't need something like the PEG tube. You wouldn't have to do that installation at that point. So much easier to get even more people in there and out and doing other things and such. So we see other applications. There's also the emergency applications that we use in hospitals. We're going to have emergencies eventually in space. Stuff have had very few so far, but we'll need, the technology will probably need to be available anyway for those scenarios. So we've got some other ideas of systems or where you could apply this stuff. But so it's not all just necessarily Mars or a series or going out from there stuff. It's a matter of scale, which is what we like about this. It's good for a couple people or passengers. It's also, you get the equal benefits. And we've looked at, what if you wanted to send 100 people to Mars, what are the benefits there compared to what we have now? It's like, you just couldn't do it now with some of our technology. So.
All right. So, we love hearing about these kinds of studies on what to a layman might appear to be, crazy sci-fi ideas. And it's great to hear that these things could actually be reality. So if I'm a young guy looking to get into the stuff you do, looking into torpor particularly, but also just in general, I guess these other related space travel aspects, how should I get into that industry?
Sure. Well, fortunately, I think, man, now you guys, younger folks have a lot more options. It's kind of crazy. I see, I watch the industry and see what's coming out, and it's like every week there's a new company with a new idea that's emerging. So I think the opportunities are endless, either to launch your own company and pursue it, stuff. So that's great support, I think, right now for doing that, and interest in it. As space becoming that is the next big thing. It was all internet.com was kind of where most of the focus was when I was coming out of school or in school and such there. And I wasn't very interested in that, still interested in the space side and stuff. But so it's great to see how much enthusiasm there is and kind of push to really take all these things we've seen in science fiction and actually I want that now. I'm tired of waiting, and a willingness of backers and investors and stuff to help support that and pursue it as kind of the next thing. So I think so many options. The prime, kind of traditional, we call them aerospace contractors and companies are also engaged too. So it's not just the smaller entities. So Lockheed, Boeing, Northrop are all pursuing these things too. Stuff. So I think it's almost you just decide what type of environment do you want to work in and stuff. Small kind of startup or a bigger entity, and there's pros and cons and affects where do you want to live and stuff too. So so those may be some of the bigger, almost more practical decisions. Is just making that those sort of choices stuff. So it's it's exciting to see.
It's awesome to see the enthusiasm and how rapidly it's all progressing now. So one other thing that we always like to try to ask people here is if there anything that's totally out of your wheelhouse that you would like to hear somebody that does it every day that from a science fiction perspective. So some idea in science fiction or some research idea in general that you would like to know more about as somebody that is very busy working on space that you don't have the bandwidth to go through and feel like you can fully absorb or learn about.
Yes. Let's see. Yeah, with things that I'm always interested in trying to read on, but never really have the time to fully appreciate or understand, I guess. Definitely watching things like the quantum computing and
Sure.
some advances there, and what is that really going to mean for computers or our capabilities in 10 years or 20 years?
Sure.
We can do things now that were Ph.D. thesis projects in 20 years ago or such, and now they're homework problems. So what is everything's always changing, everything's always advancing. So what is the capabilities going to look like there? Stuff. So I think quantum computing, AI is very interesting. It's gone a couple different paths and stuff. So what really is the future there? And I don't fully understand. I have a minor in computer programming stuff, but I still don't understand how the AI systems really work. Stuff. So I haven't had a chance to delve into that, but I think that's fascinating. I think there was this idea that we'll have this monolithic AI sentient, computer, data from Star Trek sort of thing, and now it's become much more kind of application seems specific. Of we can make AI to do certain things, but are we going to get this, integrated capability, some master program that can do, think 10 times, 100 times, 1,000 times faster than we can and kind of know everything stuff. Is that ever going to happen or such? So I think that's fascinating. And then I know on the technology side, I still think really cool. It seems to never quite get there is the metastable metallic hydrogen as a propellant option for space flight. So I tend to check in and keep track on that every once in a while. That's taking hydrogen and, they compress it to just crazy levels, millions of PSI, and try and get it to go to a metallic state. And they think if they can then relieve that pressure and it will remain in that state, so that's the metastable part. we can do that in mass. It's a crazy amount of energy that we could use as a rocket fuel. So going 3 or 4 times the ISP of something like the space shuttle main engine. But I also mentioned that was an exponential function stuff. So we can play some games with like, hey, if it was this and we had this ISP, you can do some pretty wild things with rocket and space flight if you have that. But they're still trying to just prove that it exists, in the lab level. Like we made one molecule of it, and then they're like, maybe not. Okay, we're not sure. It disappeared. It wasn't stable, so now it's gone. So we're not sure what we made. Stuff. So I'm always kind of watching that. That's probably 50, 100 years out before not only to synthesize it, but then actually can we do that in mass and fill up a tank with it or such. But that'd be cool. And I think there's been, that some of that gets mentioned in science fiction, these, sort of advanced propellants or things, so.
For sure. I'm going to restrain myself here. I'm looking at getting my master's in machine learning, so I could talk about that all the live long day. So I also am excited to see what happens there. And then so I just want to say, like, thanks a ton for coming and talking with us. It's really exciting to hear what you've managed to touch in the aerospace industry and to hear how much it's grown in just the last 20 years. And where things are off to. I'd kind of like to end. Is there anything you'd like to promote, be it a person or a book or an idea or just something to do with SpaceWorks or a project?
Yeah, I'll mention because of my kind of enthusiasm and interest in seeing this work go forward stuff. I have started a nonprofit called the Human Torpor Fund, and we're funding the research in this area stuff. So people would like to donate, it's 501c3 charity, and we're funding research grants to advance this stuff. We see a lot of the community has trouble like getting focused research in this area. So things from like National Institute for Health stuff, they got to compete with everything that all the problems of the world. So we're trying to focus some specific research grants to enable this in the future. And so you can go to our website, and your listeners could, if they feel inclined, can make a donation there. Would be fantastic. And you're contributing to maybe the future of space exploration in a small way.
We will definitely put the link to that in the show notes for the show, so people can go check it out.
Great.
Well, cool. I think that's all. So thanks a ton.
Yeah, no problem. It was good talking with you guys.
Nice too. And that's a wrap. So thank you so much for listening to this episode of Sci-Fi to Reality. We hope you enjoyed it. We also hope that you go check out our website, www.sci-fi-to-reality.com. That's www.sci-fi-to-reality.com. You can also go check out our Facebook page, Twitter, Instagram, the whole gambit. And you can also find this podcast wherever you personally get your podcasts, along with our YouTube page. I hope that you guys enjoyed it. Give it a share, comment, like, subscribe, all that good stuff for the various recommendation algorithms. We really appreciate it. Thank you so much for listening, and we'll see you in the next one.